Today's topic is axial tension and compression. Displacements in statically determinate systems. I have prepared 3 examples. In the previous video, I solved the first example. Example 2. Calculate at what distance x the concentrated force P should be applied, so that the elongations of the bars cause a parallel displacement of beam AB downwards. All bars have the same circular cross-section. The length L of those bars here and the force P applied on the beam are given. Reactions in the bars are along the axes of the bars, just as always outside the system, as if we are applying to cut it. We have 3 bars, which means 3 reactions, N1, N2, and N3. We have available the sum of the projections of forces on the x-axis, the sum of the projections of forces on the y-axis, and the sum of moments at any point. So we have 3 equations of static equilibrium. And we have unknowns, 3 reactions and also the distance x, so we have 4 unknowns. So in addition to our conditions of static equilibrium, we will also have to utilize the geometric conditions, that is, from this parallel displacement of the beam. But that will come later. First, we establish the conditions of static equilibrium. We can start with the sum of the moments. It can be at point A. When we calculate the sum of moments at point A, N3 will be in the equation along with P. The force P times the arm x causes a clockwise rotation. I assume that clockwise moments are positive. When calculating reactions and forming the sum of moments, we either take clockwise as positive or counterclockwise as positive. We will get the same result regardless of how we assume, but we have to set something. I assume that clockwise moments are positive. The force P causes a clockwise rotation, so we use plus. Minus N 3 times the total length, here 2L, which is the arm of the force, equals 0. From this, we calculate that N3 equals 1/2 P times x. The sum of the projections of forces on the x-axis equals 0. When we project force P onto the x-axis, we have nothing, we have 0. When we project N3 onto x, we also have 0, so there will only be minus N1. Now, regarding the projection of force N1 onto the x-axis, I always reason like this. If we would make a component y and a component x here, that component corresponding to the angle, which here would be the component y where this angle is noted. This component is with the cosine of that angle, with the cosine of 60, and the other component is with the sine. So N2 on x is also, and if we have the angle here, then here is the sine of that angle. So we have minus N1 times sine alpha plus N2 times sine alpha. Both are with sine because the angle is with the second component. By moving N1 to the other side and dividing by sine alpha, we find that N1 equals N2. The sum of projections on the y-axis equals 0. Now N1 is with cosine and N2 is with cosine. Both are acting as if in the direction we have adopted the coordinate system with y up and x to the right, which is standard. So N1 cosine plus N2 cosine minus P equals 0. We move P and N3 to the other side. We substitute 1/2 px for N3. We substitute N1 for N2 since N2 equals N1. And here we would sum it up, thus it would be 2 times N1 times cosine alpha divided by 2 times cosine alpha. And we have calculated that N1 equals this, and N1 equals N2. Oh, and cosine 60 is 1/2, so there's a little simplification here. In the denominator, we get 1, so N1 equals P, and in parentheses, 1 minus 1/2 x, and N1 equals N2. So N2 equals the same amount. Therefore, we have N1, N2, and N3 calculated. So we can move on to the geometric condition. I will return to this slide. We can move on to the geometric condition, which states that the beam must move downward parallel, which is our beam AB. Someone might say, then the extensions of these 3 rods should be the same. Unfortunately not. Unfortunately not. It is not the easiest geometric condition. we need to extend the axes of these rods N1 and N2. And the extension of rod N3 is vertical downward. And the extensions of rods N1 and N2 are along the axis of the rods. So this condition will look like this. We have the extension of one rod, the extension of the second rod. The line of permissible displacements of these rods is in a direction perpendicular to the extension. So this is the line of permissible displacements of the second rod. This is the line of permissible displacements of the first rod. And where they meet, these lines of permissible displacements, here I marked A, will be where the end of beam A moves. This is the displacement of the end of beam A. A marked as F_A. And the displacement of the end of beam B is simply the extension of this rod delta L3, because the extension along the axis of the rod here is no problem. So F_B, and the condition is that F_A must equal F_B for the beam to move parallel here. So F_B is simply delta L3. And from this triangle, I have transferred the 60 degrees, which are the vertex angles. Here is a straight line, a vertical, so these are the vertex angles. And from this right triangle, we can state that delta L2 to F_A is cos 60, and cos 60 is 1/2. And multiplying across, we have that F_A equals 2 times delta L2. So F_A equals F_B, which means 2 times delta L2 equals delta L3. The formula for elongation is the force in the rod times the length of that rod divided by Young's modulus times the cross-sectional area. The force in the second rod, which is N2, we calculated from the equilibrium equations. So delta L2 is that force times 1 meter, or times L, divided by Young's modulus times the cross-sectional area. The cross-sectional areas of the first, second, and third rods are the same according to the problem statement, as are the Young's moduli. And the force in the third rod was also initially calculated, meaning delta L3 is that much. Now we return to this condition and write that 2 times delta L2 equals delta L3. We multiply through these denominators so that they cancel out. We divide by p, so once we divide by p, we will be left with just numbers and x. Well, I won't go overboard with these simplifications here. We calculate that x is 4/3 meters, so 4/3 times L, which is 4/3 meters. And that's all, that's what they asked us for. At that distance, x was marked on the left side, meaning the force P should be applied at that distance on the left side for the downward parallel displacement of beam AB to occur. The whole beam was 2 meters. 2L was marked L as 1 meter, so 4/3 is 1 1/3, which means the force P should be positioned just past the halfway mark. And that's all. We can move on to the third example in the next video. If you have any questions, feel free to write in the comments. For now, that's all in this example. Thanks, bye.